Hi, so this is going to be the review of the urinary system heading into the next test. This is going to be based off that study guide, page 1. So let's go on to the basic structure of what we are doing here. So the urinary system is meant to do a couple of things, and that is filtrate and excrete a lot of metabolic waste that are, through the process of catabolism of proteins or hormones, excess water, volume within your body. So we're trying to excrete, filter out some of these, molecules, and we're also trying to regulate blood volume with through these processes. So to start with, let's take a look at some of the major components of the urinary system, and that is the kidney, the ureter, the bladder, and the urethra. So the filtration, most of the filtration happens within the kidney, and once that happens, then we deliver uh, the urine through the ureter, and then we go into the bladder where it is stored and then released outside of the urethra through micturition. What are the functions of the kidney? Again, our main goal is to excrete uh, any type of organic waste from your body. Let's think of, proteins. When you are breaking them down, you will create metabolic waste, more so known as, urea. Um, and this can be toxic to the body. So you want to release it. So we're going to excrete it, we're going to eliminate it through a process that is called micturition. And the urinary system will also regulate the amount of a volume of water that is being absorbed or excreted so that we can have appropriate blood pressure. And that is what this is related to, blood volume. Know the specifics regarding homeostatic regulation of blood, and that is blood and blood volume. So we have a couple of tools within the kidneys to help with this homeostatic regulation. So one is blood volume and the other one is blood pressure. So when we don't have enough blood volume, and that is leading to a decrease in blood pressure, we can help, the kidneys have a couple regulatory parameters so that they can hold to more water and prevent loss of water in the urine. Now we can also increase oxygenation in that circulatory system by creating more red blood cells, and we do that through the release of a hormone that is called erythropoietin. If there is not enough pressure within the system, we can use another hormone that is called renin. Renin, in it of itself, does not cause vasoconstriction, but it plays a role into the RAS system, the renin-angiotensin-angiotensinogen system. So within this system, just keep in mind, a big picture, we have renin that is released by the kidneys when we have low blood pressure, and we are going to then affect angiotensinogen. Angiotensinogen is free circulating in blood, but it's not active. This molecule doesn't do anything in and of itself. But once renin comes into place, it converts it into angiotensinogen 1. Angiotensinogen band, once it is in circulation, is then converted into angiotensinogen 2 by a molecule that is called a angiotensin converting enzyme, ACE. And this angiotensinogen 2 is the one that actually plays a major role in the vasoconstriction of those vessels. The one that we want to actually vasoconstrict is going to be that efferent arteriole within that corpuscle, within that nephron. We'll take a deeper look into this process itself. We'll revisit it again, but uh, going back to answering the question here is not the specific of homeostatic regulation of blood. We can use hormone activation to make sure that we are filtrating the right amount of blood, that is not too much, so that we can control actual blood pressure. Um, the next one is it regulates plasma ion concentrations. Within the kidneys, we are able to use hormones to make sure that we're not losing too much of the salt or like sodium chloride or too much potassium, and we can adjust through hormonal regulation how much of these we're actually excreting. We can also adjust calcium uh, concentration, and that is through also the regulation of hormones such as calcitriol and PTH. We'll take a look specifically at the part where this is happening. It doesn't happen throughout the entire kidney, but specific sections of the kidney. How does the kidney stabilizes blood pH? The kidney, throughout its filtration process, it can control the loss of hydrogen ions. The higher the concentration of hydrogen ions, the more acidic, the lower the pH is. And bicarbonate, remember that is a buffer system that it allows for the uh, increase of, or like the buffering of that acidity system. So how does the kidney stabilize blood pH? By allowing the increasing the excretion of hydrogen and bicarbonate in the urine. All right. Next question is, what major ways does the kidney filter? One of them is urea, uric acid, and creatinine. So mostly nitrogenous waste. Whenever we're processing proteins, we're breaking them down, we're releasing a nitrogenous waste. Some of them are urea, uric acid, creatinine, amongst others. But these are the three major components. Water, make sure you know the wastes. We want to filter those out because they are waste. They are not utilized by the body in a meaningful way. How do we measure the level of those nitrogenous waste in your body? Well, we have a blood test that is called the BUN, and it's measuring blood, urea, nitrogen, and it measures the amount of nitrogenous waste in your body. And you can tell that if the level rises in your system, then that is problematic because it means that your kidneys are not filtering it, filtering blood the way it's supposed to, or there is an increased production of BUN, if of blood in urea. So if the urea increases, if the nitrogenous waste increase in your body, that is going to cause to a condition that is called azotemia. Azotemia is related, it has different stages. It's a very complex disorder, but just know that it progresses as the BUN level increases, meaning that there is more nitrogenous waste in your body. Your body is going to become more, that urea is toxic, so that toxicity level is going to increase, and as it increases, it can cause major issues. We'll start with something like diarrhea, nausea, vomiting, and then it may lead on to arrhythmias, death even. That covers all three components, all four components. Okay. Next is know the anatomy of the kidney. So here, remember that the kidney is composed of a couple of sections. The renal cortex is the outside of that kidney, and here is where we have that filtration process, where we have the nephron, all right? That corpuscle, is the main component of that nephron of the corpuscle. And it is this section right here, like throughout. You can see, make it blue. All this section right here will be the renal cortex, and this is where all the nephrons will be housed. All right. Now the next portion is the renal medulla. The renal medulla here is going to be the center, and within the renal medulla we now have the pyramids. These are the structures that will house the collecting dots from the nephron itself. All right, so we have two different layers. We have the renal cortex, we have the renal medulla. Within the renal cortex, we have the nephrons, most of the filtration units. Within the renal medulla, we have pyramids, and within the pyramids, we have actual collecting dots, and we have a lot of capillaries within this section, and here is where we help with most of that water reabsorption. In between these pyramids, you're going to see that we have the renal columns, and it is within these renal columns that we have blood vessels traveling to the cortex and from the cortex. So those vessels traveling to the cortex will be arteries, and the vessels going away from the cortex will be veins. All right. As we are filtrating the blood that is going to the cortex and it travels down through the renal pyramids, we'll get to a section that is called the renal papilla, which is the very end of that renal pyramid. This renal papilla, what it will do is it will collect the urine, and then that urine then will drop into a minor calyx. The minor calyx is that major collecting duct right after the renal papilla. Once we join multiple renal, a, multiple minor calyxes, then we will have a major calyx. All right, this will be a major calyx, it will be a major calyx. And once we join these major calyxes, then we have the renal pelvis, right, the hilum, and that will lead to that urine to be released through that ureter. Quick summary: we we are trying to filtrate blood. We're trying to filtrate the nitrogenous wastes out of your body. How do we do that? By bringing blood to the kidney. We do that through the renal artery. The renal artery then will divide into smaller and smaller vessels to get to that cortex. Once it is in that cortex, it will be filtrated to filtration units such as the nephron. The nephron will filtrate that and will start creating the urine. The urine then will start being produced, and it will start going down here into that renal papilla. And the renal papilla will go to a minor calyx, then to a major calyx, then to the renal pelvis, and then out the ureter. Farther out, outside of this picture, remember that it will go through the urinary bladder, and then will go through that urethra itself. This is just a verbal structure what we just went over. So what is the renal cortex? It's the superficial portion of the kidney, and here we house most of the nephrons. All right. Now, as we look into the renal medulla, which houses both the renal columns and in the renal pyramids, we have the renal pyramids, all right, that contain the renal papilla, and they project onto the calyxes. What is within the renal pyramids? We have collecting ducts that project from the nephrons. So as we are filtrating the blood through the nephrons in the renal cortex, there will be components or tubules that come down, and there will be collecting ducts. The renal columns are the dividers of those pyramids. And what is going through them? Well, vessels. Those are the vessels that go in and out of that cortex. Nephrons. Nephrons are that filtration unit of that are housed within the renal cortex. What we're trying to do within the nephron is get rid of the waste, conserve what we need, and we do that through hormonal stimulation, passive stimulation, and we'll dive into the next one. But these are the major structures within the urinary system. Next is describe the flow of urine through the kidney. Let's go let's go through each one of the structures one by one. So remember that we have blood going into the afferent arteriole, and that afferent arteriole is going to deliver blood to that corpuscle. And the corpuscle which is made out of afferent arterial. We're gonna put in here then corpuscle. Then we're gonna divide this corpuscle into two sections: Bowman's capsule and we're going to divide it into the glomerulus. All right. Now, the glomerulus is the actual capillary itself, and Bowman's capsule is that actual bilayer that will be hugging that glomerulus. So you can think of the afferent arterial. All right, you can think of that afferent arterial. So the afferent arterial will be bringing blood into that a glomerulus. The Bowman's capsule will be hugging all of these ones, all of these capillaries. So that glomerulus is the actual capillary, and as blood is being pressurized, okay, blood is being pressurized through here, it will go into that capsular space, and that will be your filtrate, what you're trying to filter out. Once that blood is clean, it will leave out the efferent arterial. Remember that blood is not supposed to get into that capsular space. We're not trying to get rid of red blood cells here. We're trying to get rid of waste. The capillary membrane that is specific to the glomerulus is something that we need to know, and we'll discuss that later on. But just know that as we bring blood to that glomerulus, we're filtering the waste out. And once that blood is clean, so to speak, then we leave down the efferent arterial. Now, that is the path of blood. Now, this filtrate that is down here is going to start through something that we call the proximal convoluted tubule. The proximal convoluted tubule is going to make major reabsorption of nutrients. So we got rid of a lot of sugar and organic compounds, sugar, we got rid of water, we got rid of amino acids, a lot of organic compounds left blood to get into the urine. So whatever is in the tubule is what eventually will end up being in your urine, what is urine out. So this is what was excreted into the tubule. Okay. So as it comes down, we call this first portion of this section the proximal convoluted tubule, and that is because it is closest to this to that corpuscle. All right, it is closest. And as we go down, we continue. Sorry, let me just continue the same color. We're gonna then go into a loop, and that loop is what we call the nephron loop or the loop of Henle. We divide it into two sections: the descending limb of Henle, the one where there is a tubular filtrate going down towards the pyramid, and as it circles up, then we deem that the ascending limb of Henle, and that filtrate will just now go towards the cortex. We'll just keep in mind that there are different processes happening in each one of these sections. Let's keep a big picture. We're filtering blood out through this filtration unit, the nephron. So we bring blood through the afferent arterial. Once it filters out that blood, it's gonna go through the efferent arterial. That filtrate is gonna then go down that proximal convoluted tubule. Then it goes into a loop, and that loop is divided into two sections: the descending limb and the ascending limb. And once it goes up, the next portion after that, it's another limb that we call the distal convoluted tubule. We'll rehearse it again, but I just wanted to just give you a brief introduction about this. So once we are leaving the distal collecting tubule, Then we're going to go into a collecting dot, and this is the little portion right here. We have the capsular space, and once we filtrated that filtrate, then we're going into the proximal convoluted tubule. Then we're getting into the loop of Henle. Remember the descending and the ascending limb. And then we're going to the distal convoluted tubule. Here is where we have most of hormonal action. And this is all the nephron right here. Then we're going into the collecting ducts. From the collecting ducts, we have the filter that is actually going to leave your body now. And then we bring it down to collecting ducts, which are within the pyramids, right? So we have the cortex right here. We have the pyramids, we have the columns. So now we're going into the six. So the collecting ducts are right here into the pyramids. Now, as we are going down to the filtration, we're going into the renal papilla. And from the renal papilla, it's then released into the minor calyx. Multiple minor calyxes together form a major calyx. Once those major calyxes form together, then you have the renal pelvis. Then you will go into the ureter. Then you will go into your bladder, and then you will release the urine through micturition. Okay, so this is just a little breakdown of some of those structures. Remember that the renal papilla is at the end of that renal pyramid, okay, and it cusps into, it ends into a minor calyx. Right, so this portion right here is to show also the flow of blood through the kidney. So we discussed it just briefly, just a second ago. But the idea is that we have the kidney and we're trying to filter the waste out. We're trying to get rid of whatever we don't need. So we need to bring blood into the kidney, and we do that through the renal artery. As we're bringing blood into the kidney, we don't just put the filter right here, but we have to deliver these to the different filtration units, the nephrons. And we do that by dividing the renal artery into the different portions. So segmental will be the arteries that come right off of the renal artery. Then we're going to go into interlobar arteries, which are arteries that are in between the pyramids. So if you're asked what type of vessel it is flowing through those renal columns within the renal medulla, you will say the interlobar arteries. As soon as they wrap around, let me make that right, let's make it purple. When they wrap around, they change name, and now we have the arcuate arteries. The arcuate arteries then will go on to have radiate arteries or interlobular arteries. The interlobular arteries then will have offshoots of themselves, which are the afferent arterioles that will feed onto that nephron description that we just spoke about. Now, although it is a capillary that we're filtrating, um, it is not an actual capillary bed where we have actual venules just yet into that nephron loop. So we have our arteriole filtrating the blood out, and when it leaves as a still arterial. All right, so it doesn't leave as a venial. So it comes in as an afferent arterial, and it leaves as an efferent arterial, but it's not a venial because we haven't gone through the process of a delivery of oxygen or deoxygenation. It is later on in that capillary that then, after the glomerulus, then we go to peritubular capillaries, and then now we have venules. In that exchange, then we'll go through interlobar veins, arcuate veins, interlobar veins, and renal veins. And they're in the same position as the arteries. Now, we talked about some of the flow of urine through the kidney. We talked about the flow of blood through the kidney. Now, let's talk about how is it that the actual um, filtration occurs. And this occurs within the main structure that we mentioned a couple of times, and that is the nephron. The nephron consists of two parts, the renal tubule and the renal corpuscle. So the renal tubule is where the filtrate of that nephron is leaving into that pyramid. And the renal corpuscle is that Bowman's capsule, that bilayer, in addition to the capillary that comes in and out. All right. So just put in here, the filtrate will be through here, and this filtrate, once it is passing to that loop of Henle, the convoluted, then it will go right up here. And it is this part right here that we call that renal tubule. It's a long tubular passage that begins at the renal corpuscle and ends at the collecting duct. The proximal convoluted tubule, loop of Henle, distal convoluted tubule, each has their own function, and we'll discuss them next. Okay, so the renal corpuscle. So we have two sections of it. We have the glomerulus, which is the actual capillary, and we have the capsule, which is Bowman's capsule. That is a bilayer that is surrounding those capillaries. So what is happening here? We want to filter out the waste molecules, organic materials that we don't need in your body. So that waste. So as the blood is coming in, we just make sure that we have our bilevel layer. Okay. So we have blood going in through the afferent arteriole, and this is pressurized in here, leading to filtrate, leaving the capillary. We do this through a fenestrated capillary. There is a layer, there is an actual, a visceral epithelium layer, membrane, a filtration layer, a filtration membrane that helps the excretion of materials that we want to. We don't want to get rid of red blood cells or plasma proteins. But overall, we are delivering blood to this glomerulus through the afferent arteriole, and it is leaving through the efferent arteriole. A good way to remember is A for access, E for exit. Oftentimes, the afferent arteriole is smaller than the efferent arteriole is smaller than the afferent arteriole, and that is because you want to increase filtration. The only way you can increase filtration is by reducing the size of that efferent arteriole. If that efferent arteriole is smaller in size, you can see that there will be backup of blood into this section, creating that pressure so that we can get rid of the waste. As blood is coming in, it will circulate through those capillaries, but if the exit is smaller, then it will create backup pressure, and that will lead to that filtration pressure. So again, the glomerulus is the capillary itself, and it has a filtration membrane. It is characterized by having fenestrated capillaries or pores so that we can filter out those organic molecules. The efferent arteriole is smaller than the afferent because of that pressure description that we talked about. Now let's talk about the Bowman's capsule. So Bowman's capsule is divided into a couple of sections. So let's just draw it right here. And you can, although it looks circular, you have to keep in mind that each piece of the inside of this layer is actually connected to the capillary. So the insides will look like actually lined up like this. All right, side by side. And what we're trying to do is create a space so that we can collect all that filtrate and bring it down into that proximal convoluted tubule. That filtration layer has something that we have the visceral epithelium, and it has podocytes. Podocytes are the cells that are hugging this glomerulus right here. We'll take a picture in a second. But we have podocytes here, here, on top of that a glomerulus. And within that filtration membrane, we have three layers. We have filtration slits, we have podocytes, and we have a basal membrane. This is a picture of that a nephron. Here we're bringing blood through the efferent arteriole. You can see that it's a little bit larger than the efferent arteriole, but as blood flows through, it starts to back up because there is an obstruction here. Is smaller. The diameter of the exit is smaller. So the blood flows through and is somewhat pressurized. And that is going to lead to the filtrate to leave into that capsular space. You don't want to start filtrating out or getting rid of red blood cells, and that is why we have a filtration membrane. The podocytes are the cells you can see right here that have finger-like projections. And these finger-like projections allow for the hugging and allow for better filtration. So the insides, although I drew the Bowman capsule as circular, you can see that it's not circular inside. It's just that it's hugging each one of those membranes. All right. We will talk about the glomerular juxtaglomerular complex in a second, but you can see another big remark, and that is that the proximal convoluted tubule is the one that first meets the glomerulus, and then the distal convoluted tubule is the one that ends up wrapping around here. The filtration membrane. So the glomerular capillaries are fenestrated, and that means that we have pores. This allows for faster, a filtration. Now it doesn't mean that we have big gaps in between. So we have the fenestrated endothelium, a dense layer of basal lamina, and filtration slits. If there is something that injures this membrane, it will lead to the loss of large molecules from blood. So as we have the afferent arteriole leaving through the efferent arteriole, and we'll do our Bowman capsule, and I'm gonna depict it like this time. Here you can see that if we were to damage those podocytes or the filtration membrane layer in here, right at the point of contact, then the red blood cells that were flowing through, if this is broken, then the red blood cells will end up into the capsular space if there is an injury to that glomerulus, either be by diseases, medicines, trauma, but injury to that system will lead to the leakage of large molecules that were within the capillaries themselves, within the glomerulus itself. If that happens, you may end up with red blood cells in the urine, which is abnormal. This is called hematuria. If instead you end up with not red blood cells, but just hemoglobin within the capsular space, and remember that hemoglobin is a component that is within red blood cells. If there is a large breakdown of red blood cells within your body, it will lead to hemoglobin being released, and this will cause your urine to be red, not because there is blood, but because there is hemoglobin. All right. That disease is called hemoglobinuria. So hematuria versus hemoglobinuria. globinuria. All right, diving into the positioning of those nephrons. We have cortical nephrons and we have juxtamedullary nephrons. So as you can see, you remember that your kidney have two different sections. We have the medulla, it's like the right outside, and then we have the medulla. And the medulla, remember that we have those pyramids and those columns. So the cortical nephrons will be located in the cortex, deep in the cortex. But there is a transition as they get into the medulla, and those are going to be juxtamedullary nephrons. Know the difference. So the cortical nephrons are within the cortex. The juxtamedullary nephrons are they extend into the medulla. Most of the nephrons are going to be in the cortex, about 85% of them, and they are, helping with filtration. Their nephron loop is relatively short, all right? That is different from the juxtamedullary nephrons. So there are less of them, and they have a nephron loop that extends into the medulla. This is helpful because when you extend that nephron loop into the medulla, we have more capillaries in the pyramid, and it will help with the reabsorption of molecules. The loop of Henle, as we will see next, it has different sections, and we need to remember what we filter where and what we reabsorb where. But if we reabsorb nutrients, we need to collect them in blood, and the vasa recta, which is in that pyramid, in that renal medulla, will help with that. This allows the kidneys to excrete very concentrated urine. All right, so we have our cortical nephron and the juxtamedullary nephron. Here you can see that this one is mostly located within that cortex. And the juxtamedullary is now dealing into this medulla. This is a pyramid. Remember, this is a pyramid. And there are different parts to that nephron. We have the filtration unit, proximal convoluted tubule, loop of Henle, and distal convoluted tubule. It is the excretion and reabsorption of nutrients or minerals that happen within those limbs, the descending, the proximal, descent, loop of Henle, and a proximal convoluted tubule. But it is increased right here because there is more capillaries. If there is more capillaries here, you will allow for the reabsorption of nutrients a lot more. Let's take a look at the next. This is a regular, typical cortical nephron, and it has peritubular capillaries. These peritubular capillaries hug the entire nephron, and it allows for the reabsorption of nutrients throughout. We have peritubular cavities by the proximal and distal convoluted tubules, and we also have peritubular cavities right around that nephron loop, the descending and the ascending limbs. This is a juxtaglomerular nephron, and this is different. You can see how that nephron loop or loop of Henle, it is a lot longer. Remember that that will be extending into that medulla. Now this, in addition to peritubular capillaries, it has the vasa recta. Now this vasa recta picks up water ions from the loop of Henle, allowing for that extra concentration. If you are filtering out materials through the tubules and you are taking water out of those that filtrate, you're going to find that it is more and more concentrated. Okay, let's dive into the actual reabsorption and excretion of molecules. What is the primary function of the proximal convoluted tubule? The main function is reabsorption. as we are filtering out all of those that filtrate, remember that we have our corpuscle. There was a lot that left blood. Let's go ahead and label it efferent arterial. So blood, red blood cells, in addition to multiple molecules, organic molecules, sugar, amino acids, sodium, chloride, potassium, and that living blood. I'm going here. We don't want all of that. It was indiscriminate filtration. There was indiscriminate filtration. And what is living here is just basically filter out red blood cells with a lot less. It doesn't have all of those other molecules. Now, all those other molecules are needed in your body. You don't need to get rid of all of them. So that is what the proximal convoluted tubule is about. It's about reabsorbing. So all these molecules, let's go ahead and put it right here. This is the filtrate that is going to end up in urine, but you don't want to get rid of all of it. So you're going to end up absorbing it in that proximal convoluted tubule. We reabsorbed about 60 to 70% of the volume of what was filtered out. All right. So we are reabsorbing all of the glucose, all of the amino acids, all the fats, all the organic nutrients, vitamins as well. And then after that reabsorption, then we head into the loop of Henle. There is some water reabsorption here, but it's passive. All right, it's passive. There is not active water reabsorption. Okay, so the next question is describe the reabsorption that occurs in the loop of Henle. Include the different processes that occur in the descending limb and the ascending limb and the permeability of each segment. So again, we have that filtration unit, that nephron, and we have our corpuscle here. But once we have our filtrate out of that corpuscle, then we're going to get into the proximal convoluted tubule and we're going to get into the loop of Henle. The loop of Henle is divided into two sections, the descending limb and the ascending limb. Remember that the flow of that filtrate, it goes from the filtration unit descending limb to the ascending limb, and this is all termed the loop of Henle or nephron loop. There are different nutrients that are absorbed or excreted within the limbs. We absorbed a lot of those organic molecules already from that proximal convoluted tubule, the sugar, the amino acids, and the fatty acids. And there was water absorption here, but it was passive. As we head into the descending loop of the loop of Henle, you can see that it's going to be an outflow of water. And that is because around that tubule, there is a higher osmotic gradient. So water is pulled out. So because of the higher osmolarity outside of that tubule. You can see now that what is left within that tubule is highly concentrated. Now this ascending limb is not permeable to water or to ions. So there can be passive distribution. Instead, we use active transport to move some of these molecules outside. Salt, potassium, all right? So that it keeps this space highly concentrated. This is what we call that positive feedback between the ascending and the descending limb. Although we're getting rid of water first, we wouldn't be able to get rid of the water from the descending limb if we didn't have high enough concentration from the ascending limb. Summary, we're bringing, filtrate from that proximal convoluted tubule, having reabsorbed all of the organic molecules, and we're heading into that descending limb. Here's where we're trying to reabsorb water into our body. We do that because the surrounding tissues around that descending limb is it has high osmolarity. It has high osmolarity because the ascending limb has actively pushed out ions, making it more concentrated. Here you can see the gradients of concentration. So as soon as we filter out a from that corpuscle, we're heading into that proximal convoluted tubule. And from that proximal convoluted tubule, we're absorbing a lot of nutrients, but there is not meaningful change in osmolarity just yet, as we have a lot of salt, a lot of minerals in there. The what is entering here into the descending, you can see that the concentration within that descending limb is increasing, 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 and that is because we're getting rid of water. All right. That membrane in that descending loop is permeable to water. Now, as we go into the ascending loop of Henle, the ascending limb of the loop of Henle, now we have active secretion of the solutes, and that is sodium chloride. Now we're losing a lot of that concentration gradient, which we need because if the salt is out here, it allows for the water to go outside of this initial. That is again the positive loop concept that we were talking about. Let's take a look at the movement of the urine through this. So you can see that now we're getting into the distal convoluted tubule. The distal convoluted tubule now has receiving signals from other parts of your body, and that is hormonal signals. And within those hormonal signals, it can then decide to actively make changes to reabsorb calcium, to reabsorb more salt, and to decrease water. So the three hormones that you want to remember that act here: antidiuretic hormone, calcitriol, PTH, and that's it. These are the three ones. Antidiuretic hormone and aldosterone. We're gonna name for aldosterone. There is another hormone that is released, but that is from the juxtaglomerular complex, that is right around here, and that is erythropoietin, EPO, and renin. So there is a total of 6 hormones you should remember when taking a look at the kidneys. Where do these hormones act? There are actual 2 hormones that are released from the kidneys, EPO and renin, and there is ADH, calcitriol, PTH, and aldosterone that are also acting on the kidney itself. Now, once we are done through that active reabsorption of nutrients, then we'll go into that collecting duct, and there is where we're getting rid of that is urine that is going to go into your renal papilla, your minor calyx, your major calyxes, and so on and so forth. A major function of the distal convoluted tubule is selective reabsorption. What does this mean? It means that we have hormones that are leading to changes in the reabsorption. So if we have aldosterone, we will have an increased absorption of sodium, and we will excrete potassium. If we also have selective reabsorption of calcium, and that is regulated through PTH and calcitriol. We also have selective reabsorption of water through antidiuretic hormone. And here is where we get rid of a lot of the acids, drugs, and toxins. The distal convoluted tubule passes in between the efferent and efferent arteriole. So remember how we had the afferent arteriole going into that glomerulus. The distal convoluted tubule is right here, passes right here. The juxtaglomerular complex is down here. All right, we'll take a look at that in a second. Overall, the reabsorption of most of the filter occurs in one part of the nephron. All right, so most of the reabsorption of nutrients happens in the proximal convoluted tubule, and that is because we're bringing in all that glucose, we're bringing all those amino acids. Um, there is most of the water reabsorption happening in the descending limb of the loop of Henle, and that is because we have a highly concentrated tissue around that descending limb from the ascending limb actively pumping out ions, and that is leading to that passive reabsorption of water. Um, this cannot be prevented. It's obligatory reabsorption, and again, it's because your body is trying to follow osmotic gradients. All right. The distal convoluted tubule is impermeable to water. We're not making changes of water there. Instead, we're actually using active transport to get rid of ions. We could also bring some water in, but that has to be through through hormonal collection once we get into that distal convoluted tubule. Antidiuretic hormone inserts aquaporins within that distal convoluted tubule, and these aquaporins allow the free flow of water. This is complementary to aldosterone because with aldosterone we are increasing sodium reabsorption and potassium excretion. Remember that when it is leaving that tubule to go into the urine, we call that excretion. And when it is getting out of that tubule, we're calling that reabsorption. So by having more aquaporins in the membrane and by having more salt, we're going to lead to an overall pool of water into the human body. Remember all of this, what is in here is the urine, all right? And this is the distal convoluted tubule. So the distal convoluted tubule is impermeable to water, but we could reabsorb it with hormonal excretion. There are a couple of other hormones that also act in here, and that is calcitriol and PTH. But these are related to calcium balances. Next question. The juxtaglomerular complex is formed by the macula densa of the distal convoluted tubule and juxtaglomerular cells of the afferent arteriole. The juxtaglomerular complex is responsible for maintaining a homeostatic glomerular filtration rate. What are we doing here? Remember that the kidney is trying to filter out metabolic waste, such as urea. Side question, how do you measure nitrogenous waste in your body? And that is through the BUN test. If the nitrogenous waste increases too high in your blood, then we're going to end up with something that is called azotemia, that it could be very dangerous. It could lead to death. But nonetheless, going back, the kidneys are trying to filtrate this, and we monitor that filtration process through that glomerular filtration rate. It's a number. Now, if there is a decrease in that filtration or pressure surrounding that filtration unit, the kidney has a couple mechanisms to affect it to make sure that the filtration rate is sustained. Because if we don't sustain a healthy enough filtration rate, well, you can then infer that it can lead to the lack of filtration of a metabolic waste. So the glomerular complex is physically located right around the efferent and afferent arterioles. Remember that we have that distal convoluted tubule coming in between them, and we have down here we have some cells. Now we have two hormones that are acting out of this juxtaglomerular complex, and that is erythropoietin and renin. So erythropoietin is released when there is low perfusion to that kidney. If there is oxygen lack of oxygen to the kidney itself will release EPO, and EPO will lead to red blood cell production to increase oxygenation to the kidney. All right. Now the other hormone that is released is renin. Renin is actually that molecule that is helping us maintain GFR in your body. So if there is less blood volume coming into the glomerulus, well, there is going to be less filtration. And if you filtrate less, despite having less blood volume, you continue to have more metabolic waste in your body, and it's not good, it's toxic. So renin will then be released. And renin itself doesn't do anything into the kidney, but it just activates the RAS system. Renin leads to the conversion of angiotensinogen into angiotensin 1. Angiotensin 1 is then converted by ACE into angiotensin 2. And it is angiotensin 2 that then it constricts that efferent arteriole so that it can maintain the filtration rate. It's not going to increase, blood volume by itself, but it's going to maintain a stable glomerular filtration rate as much as possible to continue to get rid of waste. Here we have again the structure of that a corpuscle, and here we just need to add that, that loop of Henle. All right, and now we have our nephron right here. So remember that we have the descending limb here, and it will be the ascending limb, and then once it goes up, it will have our distal convoluted tubule. This is our proximal. The blood flow that is coming into the corpuscle, into the glomerulus, all right, if decrease will lead to the release from that juxtaglomerular complex of renin. Remember that renin, it goes on to convert angiotensinogen into angiotensin 1. Angiotensin 1 is dead plus angiotensin converting enzyme. The angiotensin converting enzyme will convert it into angiotensin 2, and this is the active form. Angiotensin 2 goes everywhere in your body and it causes multiple effects to increase blood volume, but in the kidney itself, the way it increases and maintains the GFR will be by constricting that efferent arteriole. It will also increase aldosterone from from the adrenal medulla, so that way we can increase blood volume. Remember that aldosterone acts in which section of the nephron loop? Okay, remember, just remember that it is acting on that distal convoluted tubule, and that aldosterone is increasing that sodium reuptake so we can pull more water. By doing so, we're also activating antidiuretic hormone. By doing so, we're putting aquaporins into this membrane so we can actually actively reabsorb the water so we can keep more blood volume, more water inside of our body. Remember that what is inside of this filtrate is not blood anymore. This is the urine, the waste that we're trying to get rid of. Hey, I'm up here. Okay, this is the last slide the to the part one of the urinary system, and I'll try to finish a part two today as well. So this question is: adenosine is released when GFR is 2 blank, and if its effects are that. So adenosine is not a hormone per se, but is a local signaling molecule within the kidneys. So when there are high concentration of sodium chloride within the distal convoluted tubule, then we'll release adenosine. If we have high concentrations of sodium chloride within that distal convoluted tubule, well, it means that we're getting rid of it too much. So that adenosine is to decrease GFR. All right, we're trying to decrease GFR. So adenosine is really if it's too high. And its effects are to decrease blood flow through that kidney to decrease filtration. How do we do that? How do we decrease blood flow to that nephron? Well, we constrict the efferent arteriole. So that blood that was going into that blood that was going into, we're gonna close it so there is less blood flow going into that capillary. Renin is an actual hormone, and this is released to increased glomerular filtration rate, and it is in response to a decrease in glomerular filtration rate. So when there is less, blood volume through that juxtaglomerular complex, these cells will release renin that will lead to angiotensin renin 2 creation, and this will hopefully increase blood volume, and with that we increase GFR. What is the difference between the two? So you can differentiate. Adenosine is constricting the afferent arteriole, so adenosine here, and the efferent arteriole is actually affected once angiotensin 2 is created, and it affects this efferent arteriole, and here is where angiotensin 2 plays a role.